right, everybody, welcome in. Looks like we should be getting some more people soon here. Um, so just want to go over a couple things. So I'm going to start off by getting us caught up to date on basically class overview for the next week or so, kind of leading up to the exam. Make sure everyone understands exactly how all that's going to work. Oops, looks like I'm getting blurry on the screen there. Not sure why. There we go. So just going to go over some class stuff first to make sure everyone's aware of what's happening in the next week, or really kind of 2 weeks, since next week's a big week. That's the week of the exam. So just go over that kind of stuff, make sure everyone's on the right page, and then go into the chapter about get into chapter 2, start talking about that kind of material, about the differentiation and what that's all about, and how we're gonna do that. And then that'll leave us some time later in the week to start chapter 3, which is with the material that you're responsible for the exam. So remember, under exams here, you can get information about the testing center. So if you click that, it tells you the 2 weeks that you have exams that you want to make appointments for, and then it's got a link for the testing center here. So if you click that, it's going to give you, over here it says student request form, so you can fill out a form to request your testing dates. Remember, you have to wait for confirmation because this is a request, but you can get that started. You can get that process going if you have not done it. I know most of you have. That's great. Some of you have not. And you're kind of getting to the point where you're living a little bit dangerously. Could work against you, right? And then I just want to show you, for some people I haven't seen it, and it's kind of updated now. You've got, this is the front of the my channel, this class's channel. So you can see it's got right here, it shows that this is where you would click for the live stream that's happening right now. And then down here I've created the playlist for each of my classes. So you can see right here is the playlist for VC Math V46 Summer 2023. So my morning class already has 3 classes. At the end of today, you'll have 3 classes in here. So if you miss a class or you want to watch it again, just come here, click it, watch the thing, and you'll be good to go. That's good. People have been showing up, because remember, I have to watch the rolls and drop people who aren't attending. So make sure those of you who are attending, you're doing the right thing. Make sure you're getting here when you can. So, looks like we're starting to get some more people in the stream here. So that's good. We'll work on that. That should be on mute. Okay, good. So right. So make sure you sort of link up with the testing center there. So let's see. I got my list here. Yep. So make your exam appointment, and then remember here in Canvas, so there's a few things you want to make sure you're watching these due dates. You've got, okay, today, June 27th, you have one discussion due at the end of chapter 1. At the end of chapter 2, you've got your exam 1 preparation, which is due on July 2nd. So if you click that, you'll see there's a discussion that you're going to lead about. You're going to post about how you're planning to get ready for the test. But this is one where it's also really important to read what other people are doing, right? So by reading other people's responses, you can figure out what they're doing. And you might be able to go, oh, that's a good idea. I'm going to do that too. And it might be able to help you. So don't just write yours and then move on. Make sure you actually read some of the other stuff. That's why I have this written as a discussion. In class, when we do this, a lot of times students go, oh, yeah, I see what you're doing. I'm going to try to do something similar to that. Also, you can use this as a place to form your study groups if you want to do that. And there's a practice exam in here, and you can take that practice exam to your study groups. You can also take it to the tutoring center. So there's examples on here. You see a bunch of limits that we talked about last week. Here's some limits from looking at the graph. And then there's derivatives, which we'll be getting into today and doing all that kind of stuff. So there's that. Let's see. There's a message here. So it says the discussion locked yesterday. It shouldn't have. Let's see. Do I have something set wrong? So I think you were talking about the discussion. Let's see. Oh, the chapter 1 discussion. Yeah, the chapter 1 discussion filled yesterday. But the discussion that I'm talking about is the one. So there's I may have said discussion when I meant quiz. There's the chapter 1 discussion that closed yesterday. There's the testing center quiz. I probably said discussion instead of quiz. There's the testing center quiz due today. So if you have not done that, just do it today, and you can get your points for it. And then at the end of the next chapter, there's a discussion about exam preparation. So remember, for the first test, we're going through kind of the middle of chapter 3. So first derivative test, second derivative test. So we're kind of cutting off right here. So you'll want to make sure you can do that. Now, with that said, in the homework, let's work backwards here. Was in the homework right there, looking at some problems to talk about today. So if we go in here, we can see our calendar. So notice that chapter 3 is due at the end of next week, but most of you will have taken your test before Friday, right? So that means you kind of want to make sure that you're working ahead. Don't go, oh, I have till Friday to do chapter 3, because then what's going to happen is you're going to take the test on chapter 3, and then you're going to go do the homework and learn how to do chapter 3. You want to do it the other way around. So I'm giving you time here to finish up that homework, but really if you can be working on chapter 3 earlier in the week before you go take your exam, you're going to score better on the exam. Okay, so that's definitely the recommendation, is that you do it that way. Don't wait till chapter 3's due. Try to do it ahead of time. I'm just giving you here some extra time to finish up those assignments, especially since it's only half the chapter. So at least 3.1 and 3.2, try to do it earlier in the week. You don't have to do all of chapter 3 earlier in the week, but at least do the part that you want to do before you take the test. Okay, do that. And then you can see we're working through chapter 2 now, getting into differentiation, which we're going to be talking about today. There's quite a bit of stuff there. There's a lot there, but you've got the videos posted in Canvas. You've got the videos that accompany most of the problems in the homework, and that kind of stuff. My throat's getting so sore from on these days where I have my morning class and afternoon class. I'm talking so much, like my throat keeps getting sore. Okay. Right, so there's a question over here on the YouTube chat. What units are on the first exam? Right, so probably you wrote that before I went over it, but just to kind of recap, it's everything up to and including the first half of chapter 3, so up through the second derivative test. So you'll want to know the second derivative test for the exam, but the second half we'll take care of afterwards. And I know we move so fast in the summer. I wish I could push some of these dates back. But in order to finish the class in 6 weeks, I just can't do that. We have to make sure that we're moving forward and knocking out these chapters, or we won't finish in 6 weeks. And we have to finish classes. Otherwise, it puts our transferability in question. And of course, you all want this class to be transferable. So unfortunately, we have to kind of move at lightning speed in the summer. Okay, hopefully that answered the questions there. Also, so regarding messaging me, so I'm having many students messaging me, which is good, and I'm able to get back to students. Many of you are very good at what I'm about to describe, but for the ones who are not, I just want to give you some hints so that the communication between us will be much more productive. So it's really helpful when you give me lots of information, lots of details in an email. I can help you much quicker. I had a student this morning, I think it was in my other class, my college algebra class, but she was very specific. She said, I'm working on, I forget what it was, but I'm working on problem number 10 in the homework section 2.1. Here's my work that I've done for the problem, and it keeps telling me I'm doing it wrong. That was great because I was able to look. I actually knew it then because she was so detailed and she showed me her work. Before I even looked at the problem, I knew what she did wrong. And I was able to just double check, look at the problem, and go, yep, here's the issue. And I got right back to her, and she was able to get right back to work and keep going. So that's really helpful. I'm also sometimes getting emails where people are saying things that I can't really pin down what the problem is, right? If you tell me, oh, well, I'm having trouble with factoring. Well, that's a really broad question. There's not much I can respond in an email to help you. So please be very specific. If you're having problems finding something in Canvas, or I'm having some people saying like, well, I'm not getting Canvas to work right. If you take a screenshot, it's so much more helpful because then I can see, oh, I know exactly where you are. I know exactly what your problem is, and then I can answer that question for you. So so please be detailed when you get a hold of me through the Canvas messaging. Okay, there's a question here. Is the exam going to be multiple choice? Yes. So the first exam in this class is multiple choice. The second exam is not. And I somehow forgot to do this yesterday, but basically when class ends today, I'm going to go to the bookstore and just double check what Scantrons they keep stocked in the bookstore, and I'll pick one that's appropriate for our class, and then I will let you know on Canvas. I'll post there which one you're supposed to use so you can make sure you have the right one when you go there next week. And get all that taken care of, okay? And if for some reason, I know I've had a few students with scheduling conflicts, you are allowed to take a test early in this class. You are not allowed to take it late. So if for some reason you have to take it Friday of this week, I don't recommend it, but some people are leaving town. You can take the test early. You cannot come back after the next week and take the test late. It's not really fair to the people who took the test on time and then to give someone else an extra like 4 days just because they have like, well, I went on vacation or something like that. It's not really fair to those people. So so you can take it early, can't take it late. The exam will be similar to the practice test. So it will be similar. So if you learn those problems on the practice test, you should be pretty good to go. For this first test, there will not be partial credit because it's multiple choice. So you kind of either filled in the right bubble or you didn't. For the final exam, there will be partial credit. That's the one where you're actually going to fill in all the problems, and I'm going to sit down and grade them, and there'll be partial credit on that. But the first test will not be partial credit. So double check your answers, make sure you're confident about your answers, all that kind of stuff, okay? What's going on with my speaker here is getting some interference here. I think that did it. Any other questions? Okay. Then let's move ahead. I think I'll wait a little bit longer before I take roll. So let's see what else we got here. I got that. Talked about that. We'll do roll call and Scantron. Okay, great. I think I covered all those things I wanted to talk about. So we left off last time. We were talking about limits, and then we were sort of getting just introduced into the definition of, we talked about continuity, and I believe I showed you the definition of the derivative just so you could kind of understand where we were going with things and why the limit was so important. Okay, so it's really important that we get a sense of that. All of these topics in Chapter 2 are pretty big topics. They're not ones that you're just going to like go over in an hour and get the hang of it, right? Maybe if some of you I know have taken calculus in high school, you'll pick them up quicker. But some of you, basically almost everyone, when they see calculus for the first time, these topics take some time to work through, both to understand how to do the problems and even more importantly to understand what it represents. What does it mean when you take the derivative? How does that help you figure out how to price your product? How does that help you figure out if you should buy more ads or not, right? I mean, that's a good way to sort of understand why we want to be able to analyze these functions. Let's say you have an ad campaign. Well, how do you know that you should spend $50,000 on that ad campaign or $2 million on that ad campaign? How do you know? What's the right answer? And as we'll do some problems throughout the semester where the answer comes down to analyzing these functions using the derivative and then making an interpretation of those. So it's not just being able to take the derivative. I know a lot of the homework problems are going to be like that, but it's also about being able to understand, why am I doing this? What is the point, right? So we're going to make sure we kind of talk about all those things. All right, with that said, let me open the book here. I guess we'll jump into chapter 2. Jump into the book here. So one of the things about calculus, there's a lot of notation, and the notation can be confusing sometimes. So you'll notice here on the homework, let me blow this up a little. We have this thing called the derivative, which I'm going to talk a lot about today. But you see there's two types of notation here. For problem number 1, they have this y. We call this y prime. It's y with like an apostrophe after it. In calculus, we call that y prime. And then down here, there's this weird thing. It's a fraction where it says dy in the numerator and dx in the denominator. I can even make that a little bigger, I think. Right? So you have y prime up here, dy dx. Those are both the derivative. So while it looks like, I know we make this unnecessarily complicated sometimes. You might go, wait, why do we have two different symbols for the derivative? There actually is some good reasons why we still use the different symbols. But you just want to get comfortable with, oh, when I see this, they're asking me for the derivative. When I see this, they're asking me for the derivative. The original reason why there's two different notations is actually because, we always hear about Isaac Newton inventing calculus, and he did. But actually, there were two people who invented calculus at the same time separately. Right? It's not like now where you do something and the whole world can instantly find out about it. We're talking about a couple, 300-400 years ago, where when you did something, it took many, many years for that information to travel around the world and people to know that some work has already been done. So two people, Isaac Newton and Leibniz, I forget Leibniz's first name, but they both invented calculus at basically the exact same time. But they did it with different notations. This one, this y prime, is just kind of convenient most of the time, but there are certain problems that we will get to later where dy dx is actually more convenient. So that's why we still use two notations, is because depending on the problem you're doing, one is more convenient than the other. For now, we could just use y prime every time, but they're using the different notations to make sure that you're comfortable with both and go, oh, I get it. That's still just the derivative, so that you're not getting mixed up about that, right? Okay, I just wanted to point that out. And then, of course, there's the video and the ebook that goes along with that. So there's a lot of stuff in calculus that wouldn't be too bad if I was writing on a whiteboard. But in class, I'm going to show some stuff from the book because they do such a good job giving us visuals to look at that I'm sometimes just going to use the book, if I can get this centered well here. Should we go one bigger? There we go. That looks good. Move this over so I can see. Okay, so we have this definition of the derivative of a function. So what does this mean? So here this says m tan equals the limit as h goes to 0 of f of x plus h minus f of x over h. So remember this fraction right here, that's what we call the difference quotient. And we looked last time The difference quotient is just a fancy way of writing the slope. Okay. And we had that graph on Desmos where we took the secant lines. A secant line goes through 2 points on a graph. And as we brought those points closer together, the secant line became the tangent line. Okay, so hopefully you remember that. You can go back and look at it if you want to see the demonstration. So in the limit as h goes to 0, where h is the horizontal distance between our points, as we shrink that to 0, the secant line became the tangent line. So that's what this notation is. M, if you remember back to algebra, we generally use M to represent the slope. So M tan is the slope of the tangent line. So the slope of the tangent line of a function is given by the limit as h goes to 0 of the difference quotient. So let me just remind you what that looked like a little bit. If we've got, where did it go? Here? Here we go. So what we have here is a basic function and a tangent line at x equals 1. So we're looking at the function f of x equals x squared. And here's its tangent line. The blue line is the tangent line. Remember, a tangent line just comes in, barely touches the graph at one place and keeps going. So why do we care about the slope of this blue line? Well, look what happens as we zoom in on this part where the tangent line just barely touches the curve. Well, it's pretty hard to tell the curve from the line, right? Like out here it is, but as we get close to x equals 1, this blue line is doing a very, very good job approximating this curve. So what we do is we can use the slope of this tangent line and say, well, look, in this region right here, things are so similar that the rate of change of the red curve is the same as the slope of this tangent line right here. So finding the slope of that tangent line is really important. It's giving us the instantaneous rate of change of the red curve. And that's helpful. You can imagine it's helpful to know the instantaneous rate of change of your profit. What is my profit doing right now? Is my profit increasing? Is it decreasing? And that's not even enough information. What if my profit is increasing, but it's increasing really, really slowly? Or what if my profit is increasing, but it's increasing really, really quickly? Good news, right? But you have to be able to tell the difference between increasing quickly, increasing slowly, and that's what the instantaneous rate of change tells us. It can tell us, yes, the profit is increasing, and in fact, it is increasing very quickly. Great. That's wonderful news for our business, right? Or our cost is also going up, though, and it's going up at a slower rate. You know, these are the kind of things we want to get specific about. So that instantaneous rate of change is the slope of your tangent line, and the slope of your tangent line is the limit of your difference quotient. So with all that, we really just change the notation, and then we give it a new notation to give us the definition of the derivative. So the derivative of the function f of x, denoted f prime of x, so that little apostrophe tells us we're talking about the derivative of f, is the derivative of f of x is equal to the limit as h goes to 0 of the difference quotient, provided the limit exists. So we did all that work last week about when limits exist, when limits don't exist, how to see a limit from a graph, how to see a limit algebraically. We did all that because we need it in the definition of the derivative. We also later will need it in the definition of the integral, and sometimes we need them just for their own sake. So that's the mathematical interpretation of the derivative. That's how you calculate it. But how do we interpret the derivative? How do we think about the derivative? So the derivative f prime of x of the function f of x is the slope of the tangent line to f of x. So we have to specify a certain point. Like here in our graph, I specified, let me pull out a little bit here. We specified our function as x squared, and we wanted to know the slope of the tangent line at x equals 1. So that's where the tangent line is. So in the book, they're talking about is the slope of the tangent line to f of x, but we generally talk about the slope at a certain point. Another interpretation of the derivative is that it is the instantaneous rate of change of f with respect to x. So that's, again, we can see both of those interpretations by looking here at this picture. All right. We can see that, yeah, it's that instantaneous rate of change because it's telling us what the function is doing right in this instant. And it's also the slope of the tangent line. So we're seeing both of those. Okay. So we kind of looked at these last time a little bit, where you take your difference quotient. Remember, we covered those, and you'll have to do these difference quotients. You take the difference quotient, and then what we do at the very end is we take the limit as h goes to 0. And this canceling only works if h is not equal to 0. But that's the thing, is that the limit has h going to 0, not h being 0. That's why we don't actually care what happens at h equals 0. Remember, the limit is about getting very, very close. So when we were talking about getting close to 2, we were talking about x being like 1.999999999. We can divide by 2 minus 1.9999999. We just can't divide by 0. So that's why we did that work with the difference quotient, so we could calculate these difference quotients, then take the limit as h goes to 0, and then we get our derivative. So this makes sense if you think about this example right here. They say find the derivative of this function, f of x equals 5x plus 8. So let's take that example. I don't know why I keep getting blurry here on the screen. So what was it? 5x plus 8? F of x equals 5x plus 8. And we get this line, of course, right? 5x plus 8, that's a line with slope 5 and intercept 8. So many of you probably knew what that looked like before I put it on the screen. But here is the function for that particular problem. F of x equals 5x plus 8. It's this line. Well, think about it. What's the rate of change of this line anywhere? Well, it's going to be the slope of the line, because a line will be its own tangent line, right? So if we want to know the curve or the rate of change at anywhere along this line, it's going to be 5. That's what the slope is. So taking the derivative of a line is really, really easy, right? That's why they're kind of starting off with this one. You go through you do this whole thing, and you end up with an answer of 5. So 5 is the instantaneous rate of change. Well, yeah, that makes sense. I'm on a line with slope 5. Normally what happens is you have a curve that's going up and coming down. So at different points along the graph, you have a different rate of change, right? Maybe it's your distance graph. Sometimes you're speeding up, sometimes you're speeding up, sometimes you're slowing down, sometimes you're stopped, whatever is occurring. But for a really boring function like a line, the rate of change is always 5, right? And you can see they just took the limit of the difference quotient. Okay. So here we go. It's even worse than I sort of told you a minute ago. There's a bunch of different notations for the derivative. The first 3 are the ones you're going to see the most often. F prime of x, y prime, dy dx. Those are the ones you're going to see the most frequently. Okay, you'll see those very often. Gottfried Leibniz, that's his name. I remembered Leibniz, but I couldn't remember Gottfried. In 1670 is when both of these guys were separately inventing calculus in different setups. It's the same mathematics, but they represented it differently, which is why we have these notations. So you can have your derivative of your function and have it be a function, but sometimes we want to evaluate that derivative at a specific point, like we did over here in this picture. The derivative of x squared is 2x, okay? But we wanted to know about at a certain point. So we actually had to take x equals 1 and plug it in to get a slope of 2, right? So that's what this notation is about. This is saying take your derivative and evaluate it at a point A. So for us, that's here, that x is equal to 1, or that A value is equal to 1. We're evaluating the derivative at that specific spot. Here, you'll see this line sometimes in calculus. This line means evaluate here. And we'll actually see later in the integral calculus, when we see this line, there's going to be two values. We evaluate it at 2 points, and then we do a subtraction. But that's down the road. For now, this just means take y prime and evaluate it when x equals a. So a might be 1 or 2 or 3/4 or something like that. And the same thing here. They're saying find the derivative and evaluate it at a. That's what this means. So when you see, so for f of 5, that means take your original function and evaluate it at 5. So you would take 5 and plug it into your original function. Find f prime, that means find the derivative of this, so the limit of the difference quotient, like we've been talking about. And then this one over here says take the derivative and evaluate it at 5. So even though A, B, and C here all look very similar, there's some subtleties in the notation telling us to do slightly different things. So you want to make sure that you're paying attention and you understand the difference between those different pieces that you're working on. All right. And you can see again, it's that limit of the difference quotient. It just comes up a lot. And there's a problem on the test, oftentimes ends up on the final as well, where you have to actually use the limit of the difference quotient to evaluate the derivative. So the way calculus works, just so you kind of know how this chapter is going to unfold, we always start off by defining the derivative in the most difficult way to calculate it, which is usually the limit of the difference quotient. That's the definition of the derivative, and that's what we generally need to know how to do. But then what happens is we spend a good chunk of this chapter figuring out shortcuts, right? Which are easier ways to take derivatives than going through the whole limit of the difference quotient. So for example, we're going to learn shortcuts for taking derivatives of polynomials. And it's much easier, especially if you're talking a high degree polynomial. If I gave you like a 4th degree polynomial and said, find the limit of the difference quotient to get the derivative, by the time you finish that problem, you would probably be very frustrated. It's a lot of algebra, takes a lot of steps. It's like you'd probably fill a couple pages. It gets really tedious and annoying. And then we pull out this rule, this shortcut that says, actually, taking derivatives of polynomials is really easy if we just use these shortcuts. And that's fine. But what you want to understand is, in this class, you will probably on both exams, and on the second one, you'll have to show me all the steps. You'll have to take the limit of the difference quotient to find the derivative. So in other words, there'll be at least one problem usually on the final where you can't use the shortcuts. You have to show me you know how to use the long way to do it. But for most of the problems in this class, using the shortcuts once we learn them is completely acceptable. But you just you have to be able to know how to fall back on the things that aren't the shortcuts. And I know some people get annoyed with that and say, well, why can't we just use the shortcuts? And the answer is, in real life, not all functions have shortcuts to find their derivative. So it's great if it's a polynomial, that makes it easy. But what if it's some kind of mixture of polynomials and exponential functions and logarithms and quotients and all sorts of, it's just a really complicated thing. The shortcuts aren't going to work. You're going to have to try to work through the limit of the difference quotient in order to get that answer. So that's why it's important. Okay. Right. Okay, so now we have now we're going to mix in a little bit of concept. So we're going to talk conceptually here for a little bit. And that's going to help you get a sense of how the derivative works. It's going to give you a little bit better intuition about it, as well as being able to actually calculate derivatives. So what does this mean? The derivative of a constant. If y is equal to c, where c is any real number, then the derivative of c with respect to x is 0. In other words, the derivative is 0. Well, why would that be? Well, think about a constant function. Like, remember what a constant function would be? Let's say you had $100 in your bank account, and you didn't put any money in your bank account. You didn't take any money out. It's just going to stay right at $100, right? It's constant. Every single day, your bank readout would say $100. It's constant. Well, think about this function. What is the rate of change of a constant function? Well, a constant function is defined by the fact that it does not change. Therefore, what is the rate of change here? 0. There is no change. It's static. It's staying the same every day. So that makes sense. The derivative of a constant function is 0. If we think about it conceptually, we go, yeah, that makes sense. If something isn't changing, then its rate of change should be measured as 0. Okay, I get that. But what about formulaically? What if you took the limit of the difference quotient? Would you get 0? And the answer is yeah, because your f of x plus h and your f of x will be the exact same term because that's constant. So therefore, you get 0 in the numerator. So when you go through and find the slope, your slope is 0, right? We talked about the slope of the tangent line is the rate of change. Well, what's the slope of this line? 0. So by looking at this, we can kind of bring together the concept of why a constant function should have a derivative of 0, because its instantaneous rate of change is 0. But then also we see that in the math when it comes out, right? So that's helpful. All right, anytime I take the derivative of a constant, I get 0. All right, so if you think about it, that's part of a polynomial, right? Because when you have a polynomial, very often your last term in the polynomial is a constant. It's like a +4 or a -1 or a +3 or something like that. Well, now we know, oh, well, at least that part of the derivative will become 0. All right, all right. Here's one that comes up. We don't have time in this class to work through it, but you're going to use it all the time. It says if we want to take if we have a function that is x to a power where n is any real number, so it's x to some real number power, then the derivative is n times x to the n minus 1. Now that might seem confusing at first, but you're all going to get this really quickly, and it won't be confusing for very long. So what do we mean here? Uh-oh, did my screen freeze? What's going on here? Uh-oh, it's not letting me change tabs. Oh, there we go. It finally changed. Okay. Oh, I want this one. Okay. So let's do an example, and you'll see that this, you in a calculus class are going to have to get good at reading these formulas that like what I was just showing you in the book, but I'm also going to show you what they mean, so it helps you make sense of it. So your directions will be something like this. Find f prime of x. In other words, find the derivative I had a message there. I had to read from a student. So, okay, let's see. What does it not like? What, some kind of server error. Here we go. So we want to find f of x, but we have to be given a function. So it'll say something like, find f prime of x when my computer's doing some weird stuff all of a sudden. Let's see. Okay, find when f of x equals x to the 6th. Okay, so this is like what we're talking about. X to the n, right, is what we're talking about over here in the, so if we bring this back up, we have our function is x to a power, where n is real number, any real number. Then the derivative is n, that was our power, times x to the n minus 1. So all that means is f prime of x would be be equal to. So basically you bring the exponent down in front, and then you decrease the exponent by 1. So the derivative of x to the 6th is 6x to the 5th. All right, so let's try a couple more of these. You'll see they're pretty straightforward. So if f of x equals x to the 21st, then see if you can figure this out before I give it to you. F prime of x equals, oops, gotta put the curly braces there. So if f of x is equal to x to the 21st, so just take a second, try to figure out, okay, what's f prime of x going to equal to? Well, our formula says we bring the 21 down in front, we decrease the exponent by 1. So if I do that, it's going to become 21x to the 20th. Right, so hopefully you're kind of seeing a pattern here. Most people pick this pattern up pretty quickly. And as you can see, the two things we've looked at so far helping us build derivatives of polynomials, right? A polynomial has powers of x in it. A polynomial oftentimes has a constant in it. So we're building these tools that are going to help us take derivatives of polynomials. If y is equal to x, then y prime is 1. This makes sense if we look at our picture again. If we have y equals x, what is the slope of that line? The slope of that line is 1. So it makes sense. The derivative is equal to 1 then. Right? Okay, that's good to know. And you notice here, let's see, I want to make sure I have time to cover some more complex stuff. But notice the key here to doing these, people get confused about these root problems. The key, like I'll see people just stumble, like they'll stare at this problem and go, I don't remember us talking about how to take the derivative of something like that. And then I'll say, turn it into a fractional exponent. And they go, oh, you mean like x to the 2/3? And then instantly they see how to use the power rule to do it. So this is confusing for students. But if, like they say here, if you turn it into x to the 2/3, then all of a sudden they go, oh, so that means I'm supposed to bring the 2/3 down in front and then subtract 1 from the exponent? That's correct. So you end up with 2/3 x to the negative 1/3. And we don't leave our problems with negative exponents. So we bring the, remember we move the negative exponent to the other part of the fraction and then make it a positive. So that's why f prime of x is 2 over 3x to the 1/3. If you just jump right to here, it looks confusing. But if you see the steps along the way, and always remember, whenever you see a root in calculus, it's almost always beneficial to write it in terms of fractional exponents. Because then you can just apply the power rule, which I know I just gave it to you a minute ago, so you still might be a little confused on it. But within a day or two, you're going to know that rule inside and out. You're going to be very good at the power rule, and you're going to love when you see polynomials and you're told to take the derivative because you're going to go, that's easy. I know how to do that. Something like this where you're given 1 over x to the 4th. Well, one way to do this problem is to just view it as x to the negative 4 and then use the power rule, right? So if it's x to the negative 4, we bring the negative 4 down in front. We subtract 1 from the exponent. It becomes negative 4x to the negative 5. And then we don't leave our answer with negative exponents, so we turn that back into negative 4 over x to the 5th is how you would do that problem, okay? All right, and then we get into actually finding the equation of the tangent line at a certain point. So this is where we're starting to get into problems that involve multiple steps. Because if we want to find the equation of the tangent line at a certain point, well, what is the thing that gives us the slope the slope, or the derivative gives us the slope of the tangent line, and then that point tells us exactly what it should look like. So let's do the following. Let's do this one that I have an example for, so we can kind of follow along, right? So we already know what the answer is going to be. The slope of the tangent line at x equals 1 for y equals x squared is 2x minus 1. But why? Why is it that? How do I know that that is the slope of the tangent line? Well, let's work through it. So let's go find the equation of the tangent line for y equals x squared I don't know why it keeps giving me these errors today. For y equals x squared at x equals 1. Okay, so that could be a problem that you could be given, right? Find the equation of the tangent line for y equals x squared at x equals 1. All right, so whenever someone starts talking about a tangent line, you start thinking, well, in order to create the line, I need a slope, right? Because ultimately, we want something that looks like, this is something hopefully most of you remember from your algebra days, y equals mx plus b. That's the equation of a line, right? We're being told to find the equation of a line. Why does it keep doing that? I think their servers may be slow today. So if you're going to find the equation of a line, what do you need? You need a slope and you need an intercept. So you start going, oh, well, the slope of the tangent line, that's the derivative. So it looks like we're going to need the derivative for this problem. So we say, okay, well, if my function is y equals x squared, then that means that my y prime is equal to, well, remember our remember the power rule that we just used. Come on. The power rule that we just used says that we bring the 2 down in front and we decrease the exponent by 1. So that would become 2x to the 1. But of course, we don't usually write things as 2x to the 1. We would write that as 2x, right? So that gives me the derivative for the function as a whole, but we want to know what's happening at x equals 1. Well, then I can evaluate this derivative at x equals 1. That's what's given in the problem. So at x equals 1, the derivative is 2 times 1. Because our derivative is 2x, and we want x to be 1, so that's 2. Right? At x equals 1, the derivative is 2 times 1 equal to 2. Maybe I'll see if I can keep it from messing up more than I want it to. So at x equals 1, the derivative is 2 times 1 equal to 2. So that's the slope of our tangent line. So we now can go back and replace this m with a 2. We just use the derivative to figure out that value. So we know now that our equation should look like y equals 2x plus b. So we got the slope part. We don't know the intercept part. So now we have to figure out what b is. Now, normally when we did this in algebra class, when we had to solve for they gave us some information and said find the equation of the line that does this stuff. So you would first find the slope, which is what we did here in calculus. We still find the slope. And then we would have to figure out the intercept. And usually what you would do at this point is figure out the intercept by plugging an x and a y for a point on the graph into what our version here, y equals 2x plus b. So you go, well, do I know a point on this graph? Well, in fact, we know a point that's on the graph and the tangent line. It's the point where the tangent line touches the graph, right? Necessarily, that's what the tangent line has to do. It has to touch right at that point. So we can go, well, that means I can figure out that point by figuring out f of 1 because our value is so f of 1, we're taking our x value of 1, we're plugging it into our function, because our function is just x squared. So that means we're going to square it, so that equals 1 squared, which equals 1. So that means that the point we care about is 1, 1. The x value and the y value are 1. So we can see that if we go back to our graph, let's look, we can see that in fact the point where the tangent line touches the curve at x equals 1 is the point 1, 1. So an x value of 1, a y value of 1. So we'll plug that into our problem here. So we plug that into this version. So that becomes come on. I've never seen it act this poorly before, this software. So I apologize, it's doing that. So we know it goes through the point 1, 1. So if we have y equals 2x plus b, we have an x value of 1, a y value of 1, telling us that y, well, that 1 equals 2 times 1 plus b So if y equals 2 times 1 plus b, then you subtract 2 from both sides, and we get b equals 1. So b equals 1. B equals 1. So b equals 1. So therefore our equation is y equals 2x plus 1. And sure enough, that's what we have on our graph. Y equals 2x minus 1. Oh, right, because I subtracted incorrectly. It's 1 minus 2. So this should be negative 1. So b equals negative 1, y equals 2x minus 1. And that's what we see in the graph. Y equals 2x minus 1 is our tangent line. So see how there's a bunch of steps there? First, you find the derivative. Then you evaluate the derivative at the point that you care about, and that gives you your slope. Then you have to calculate a point on the curve at the x value that you care about, and then use that to solve for b. So there's a bunch of steps there. It's not one where you just kind of sit there and go like, it's like one thing we got to do and then we're done. It's like 4 parts to that problem, and they're not obvious, right? So the calculus is a little tricky there. But you can see we were then able to get the tangent line that we care about. All right. So you'll do some of that. Okay, let's take this opportunity to take roll. And then when we come back, I want to look at this problem right here. Actually, do I want to do that yet? Oh, we're about to do it. Yeah, okay. Okay, let's see who we got in Zoom here. All right. Okay, if you're on the YouTube stream, if you could just put in your first name and the first letter of your last name. You don't have to put in your whole last name, but just throw in, like for me, I'd put Topher F, and then I can start seeing who's here. Okay, so people I'm missing that I missed somehow. So let me know if you're here because I have you marked as not here. We've got Jasmine A, Isabella G, Clarissa H, Kyle M, Nancy R, Ashley V, and Wendy G. Okay, here we go. A couple people. Okay, Nancy R, Isabella G. Okay, so that leaves the other names. Okay, looks like we got roll taken then. Great. Okay, so we have another rule that tells us We have another rule. Like these rules all I know can look confusing if you're not used to the notation, but they're important and they're simpler than they look, right? This looks like a really complicated, fancy thing. It's really not. Um, it's just got notation that was confusing. Yeah, Bella, I got you. I got you were marked as once you put your name in, I got you on the roll. Great. Okay, so the derivative of a constant times a function. So what this says is if we take the derivative of a constant times a function, we can pull the constant out in front and take the derivative of the function and then multiply the constant in at the end. So a lot of times what happens with these derivatives is you're trying to find a way to break it down into a bunch of smaller derivatives. That's what we do with a polynomial. We break the polynomial down into where we're actually taking the derivative of each term separately. You'll see that in a few minutes. And then when you take each term separately, you break it down into the smaller components of each individual term. And so that's kind of the goal. Take something that's big and complex, break it down into smaller pieces. So what this says is, let's say I have like a polynomial term, like a 4x to the 6th. I can pull the 4 out in front, take the derivative of x to the 6th, and multiply the 4 back in. So what would that look like? Let's say we wanted to do if f of x equals 4x to the 7th, then f prime of x equals what? So if we have that f of x is equal to 4x to the 7th, then f prime of x would be what? Well, we saw a minute ago that we know how to take the derivative of x to the 7th, right? That should be 7x to the 6th. Well, that rule we just read says ignore the constant for a minute, figure out what the derivative of x to the 7th is, and then multiply the 4 back in. So the derivative would be 4 times 7x to the 6th right? We ignore the 4 for a minute. We take the derivative of the x to the 7th piece, and then we just multiply the 4 back in, and we're going to get 28x to the 6th. And we get 28x to the 6th. So that's how that derivative works. Now, that's great because if you think about it, this is what our terms of polynomials look like, right? A coefficient, a variable, and an exponent. And we already know how to take care of the ones that have no variable, the constant. We know that part will be 0. So that means that we now know how to take derivatives of the terms of a polynomial. So how does that all fit together? Yeah, we kind of talked about that. Here we get a rule that says the derivative of a sum or difference. So this says if you have a function which is composed of two different pieces separated by a plus or minus, we can just take the derivative piece by piece. Well, that's great with a polynomial. That's saying I can take my whole polynomial and instead just take the derivative of each term in the polynomial. And we just saw how to take the derivative of terms in the polynomial. We just did it here, right? We basically just did it. So let's put all that together. If, let's give myself a little room. If, let's make it g of x so we can tell the difference. G equals, I don't know, let's come up with, say, 3x squared plus 5x plus 2, then f prime of x equals Okay, so here we have a whole polynomial. We've got a function g of x, which is 3x squared plus 5x plus 2. Oops, and I wrote f again. Let's make that a g. So if g of x is 3x squared plus 5x plus 2, what is g prime of x? What is the derivative? Well, we're basically just going to look at each individual term of the polynomial and take that derivative. So the derivative of 3x squared, if we kind of look at what we did up here, the derivative of 3x squared should be 6x. So the first term's derivative is 6x. Then what about this one? The derivative of 5x should be 5. And the derivative of plus 2, well, the derivative of a constant is 0. So actually, we're done. So the derivative is 6x plus 5. So derivatives of polynomials, once you do a few of these homework problems, it's going to click for you and go, oh, that's pretty easy. Then you'll be set, right? You will love taking the derivative of a polynomial because they're very easy compared to basically everything else. Right, so you can see what's going on here. They say find the derivative of 5x cubed plus 4x squared plus 9x minus 7. And you can see they're just taking the derivative of each term individually. So the derivative of 5x cubed is 15x squared. 4x squared becomes 8x. 9x becomes 9. And the 7 becomes 0. So pretty easy to take that derivative. Then they do some problems where they're telling you to evaluate the derivative at a certain point. It's not complicated. Find the derivative, then evaluate it at a point, right? So it might look scary here, but it's not. You're just putting two things together you already know how to do. Find the derivative and then evaluate it at some specific x value. I thought marginal change came later. Let me take a look here. Is it marginal? I thought marginal analysis was in chapter 3. Let's take a look. Oh, okay, maybe I have this in the wrong place. Let's move this so that our marginal analysis is going up here because it looks like it's in this part of things. So marginal analysis is another one of those things that sounds complicated, and once you get it, you're gonna go, oh, that's it. That's all it is. It's not very complicated. So here's the idea. Remember what a derivative is telling us. A derivative is telling us a rate of change at a specific point. Okay? Well, as they say here, intervals of length 1 are very important in business applications. Why is that? Because sometimes your decision is, should I buy one more product? Should I sell one more product? Right? You're trying to figure out if you should do one more thing. Is it beneficial to my company to buy one more unit of this thing? Is it beneficial to my company to sell one more unit of this thing? Should we increase our price by 1? These are the kind of questions that you can ask, and they give you a sense of the direction of things, right? It's kind of a simplification of advanced calculus where you're kind of, calculus can be used for really, really complicated things. But in business, it's all sort of a little bit simplified because you just kind of need to know, should we do this thing one more time? Should we sell one more unit, right? So intervals of length 1 are very important in business applications. So I'm going to read this because it's pretty good understanding of it. For example, a publisher that is currently producing and selling textbooks realizes a profit of P of $5,000 from the sale of those 5,000 units. If the publisher increases the number of sales by 1 to 5,001 books, the increase in profit is P of 5,001 minus P of 5,000. I'll explain that in a second. But we can approximate this number by finding P prime of 5,000, the derivative evaluated at x equals 5,000. This approximation is called the marginal profit. So the marginal profit is the approximation of selling one more unit, right? What is the profit if we sell one more unit, right? It is an approximation to the actual change in profit brought by a 1 unit increase in sales. So what's really going on here, we've got our profit function P, right? And just want to make sure everyone saw that. There's a video in here about marginal analysis where I describe it. I talk about the marginal analysis a little bit. So you can watch that if you need to. But let's make sense of what's in the book. So P of 5,001, that's the profit from selling 5,001 units. P of 5,000, that's the profit from selling 5,000 units. So if you take P of 5,001 minus P of 5,000, that gives you the profit you made off that last unit from selling that very last unit that you sold. Okay. Sometimes this is important because your profit function changes. So in some sense, you might make more money off your 500th unit that you sell than you did off your 3rd unit that you sell. Why? Because your profit function is changing over time. Now, in reality, you don't really care, because when people come into the store to buy your product, you don't say, well, this was the 3rd one, so we're going to charge you this much, and this one is the 500th one, so we're going to charge you this much. But it's important to know when you're trying to make decisions, should we increase production? Well, how much profit are you going to make on one more unit? If it's good, if you look at that profit and go, that's good, that's worth it, then you'll increase production. Maybe the profit that you're going to make on making that next unit is very small, or maybe even negative. Sometimes making too many units can actually cut into your profit. So that's why we want to do this kind of analysis. Should I sell one more unit? Now, why would that be? Why would your profit function go down, actually, as you make more units? Usually you go, well, usually when I'm buying stuff, if I buy more units, I get a better price, right? If I'm buying paper and I tell the paper company I want to buy 500 reams, they're going to give me one price. If I tell them I want 5,000 reams, I'm going to get a much better price per ream of paper, right? So why on earth would my profit go down by making more units? Well, one good example is rare earth metals, right? If any of you know much about computers, this is a very volatile commodity in the world, because there's these rare earth metals and they're being mined in different parts of the world. Sometimes, we start bringing in ethics. United States and China and different countries are going into different countries and trying to get those rare earth metals out so that we can keep producing lots of computers and satellites and cell phones and lots of stuff like that. Sometimes it's not done in a way that is so ethical. And sometimes what happens over the years is things will happen. Maybe in a given year, a lot of rare earth metals are coming out of a certain country in Africa, but then maybe war breaks out in that country. Now all of a sudden, the price of those rare earth metals is going way up. Okay, so it could be that a company is able to get some amount of rare earth metals and sell it to you for a certain price, but if you keep saying, I want more and more and more, it gets harder for them to get that product, because there's a war going on around the mines where this stuff is being mined. So it gets more and more expensive. So it's actually getting more expensive for you to buy more rare earth metals. So as you want to make more and more computers, your price is actually going up. So, when everything is nice and easy, then usually the more you buy of a product, the price goes down. But when there's a limited supply, like rare earth metals, the price can actually spike as you try to buy larger quantities. Right? So that's why you have to ask questions like, should we produce one more unit? Well, that's what that marginal profit does for us. So the price of producing 5,001 minus the price of producing 5,000 gives us the profit on that last item. Sometimes that's hard to calculate because sometimes you might not have your full information, right? It's easy to forget that when you're doing problems out of the book and they give you some information and you go, well, here's how I'll figure it out. But in real life, sometimes you're operating on limited information. You might not have the profit function. You might somehow have the derivative of the profit function, but you might not have the original function. Well, this is saying we can easily estimate, it's not exact, but it's close estimate of that marginal profit, the profit used to, the profit that is realized by selling one more item, right? So you can see what they do here, and I just want to go over I want to give you this interpretation. So when you're stuck with these interpretations, you can look in the book and look them up. So let's say our function is y equals 6x to the fourth. They say find the derivative, and then find the derivative evaluated at x equals 3 and interpret the result. So we take the derivative. Hopefully you're kind of getting the hang of it. 6x to the fourth should be 24x cubed, right? Because we bring the 4 down in front and multiply by the 6, decrease the exponent by 1, giving us 24x cubed. Now when we evaluate that at x equals 3, we get 648. So what is the interpretation? Because remember, the reality is if you get in a position, if you're kind of want to, you really get the business calc and you kind of are able to do the math well, that opens a lot of doors for you. You will be able to work certain parts of business that other people who are weaker at the math cannot. But remember, if you're in one of those positions, there's a good chance you're going to have software that actually does the derivatives for you, but it's not going to interpret them for you, at least not yet. Not till AI gets much, much better than it is. That could be years down the road. So you have to be able to interpret what that calculus means. So here's our interpretation. If x increases 1 unit in value from, say, x equals 3 to x equals 4, then f of x will increase in value by approximately 648 units. So then you can make that decision. Should we increase production by 1? Right? For example, right? Yes, it's gonna mean that we make an extra 648 units, whether that be dollars or yen or whatever, right? So So one thing they note about the marginal change, right? The more your curve is changing, then the worse your approximation is going to be. So see how here the curve is very slight? So the tangent line that we create actually does a pretty good job covering the curve over a large area. But look here at this curve down here that is a much curvier curve. That sounds silly, but like it's more curved than the one above. Okay, see how the tangent line approximates this curve over a smaller area? So that means that your marginal approximation will not be as good. Okay, so just keep that in mind when you're trying to decide that part, right? So here's a good problem. You can read this one in the book. I'm going to move on for the sake of time so I can cover some more things. You've got your interpretation, though. Read those interpretations in the book. It's really important to be able to pick out those interpretations and make fun of them. So conditions for non-differentiability, that means when can we not take the derivative of something, right? We've now seen that the marginal cost or marginal profit or whatever is based on the derivative. So what about when you can't take that derivative? So a function f of x will not be differentiable at x equals a if any of the following 3 conditions exist. F of x is not continuous at a. So remember we had a section that you covered continuity. If your function is not continuous, you can't take the derivative. Okay? If f of x has a sharp corner, So think about like absolute value has a sharp corner in it. You can't take the derivative at that corner. You could take the derivative on these straight pieces. That's okay. But you can't take it at A, right where the corner is. It doesn't work that way. Also, if you have like a cusp, where it like kind of like a pinch point kind of here, or a vertical tangent line like that. If you have any of those, you can't take the derivative. You have to use some other stuff. Okay. So that was 2.1. I know these sections are big here, but that was a good introduction. Let's close that and go to 2.2. Okay, now we start getting into some shortcuts. And the shortcuts are great, but remember, they're not everything. You have to remember how to do the long cuts too, not just the shortcuts. Okay, so the product rule. The product rule tells us how to take the derivative of two things that are multiplying each other. So remember earlier we broke down polynomials. We said that there's a theorem that tells us we can separate a function when there's a plus or minus into the different terms and take the derivatives separately for those different terms. We do not get to do that for multiplication, unfortunately. So what this says is, let's say we have u of x and v of x. So two functions, they're multiplied together, and we want to take the derivative of that. Then you get this kind of weird formula for the derivative of the product. So the derivative of the product is the derivative of the first function times the second function plus the first function times the derivative of the second function. So that sounds confusing, but basically you've got two combinations of your two functions, and in one you take the derivative of one function, and the other one you take the derivative of the other function. So you just mix it up. So for instance, let's take this one for example. This function, you could multiply this out if you wanted to. You could go through and do FOIL and multiply this out, get a polynomial, and take the derivative of the polynomial. But sometimes you're going to run across problems where you can't do that. We haven't dealt with more complicated functions yet, but in the next few days, we'll be able to come up with really complicated functions of these where you would not want to multiply it out. You would want to use what we call the product rule. So see what they do here. They identify this first thing in the parentheses as our u of x, and the second one as our v of x. So our rule for the derivative is you take the derivative of the first piece times the second piece plus the first piece times the derivative of the second piece. So you can see what they did here. The 10x is the derivative of u. So take the derivative of 5x squared plus 4, you get 10x. And then you leave the v of x part alone. So see how it's x cubed plus 11? So we've got the derivative of the u plus v. And then we add to it, now you leave u alone, so u just becomes the 5x squared plus 4, we just write it in, times the derivative of v, so that becomes the 3x squared. Okay, and then you just sort of simplify things from there, and then you get your function. So this is one where, at least at the moment, we could do this problem two different ways. Multiply it out, get the polynomial, take the derivative, or use the product rule and get the derivative that way. There's lots of problems where you don't have a choice. You just will have to use the product rule. Okay, so it depends on the one you're looking at. So there's the power rule. I think once you watch a couple videos on it, a couple examples in the videos, you're going to go, oh, okay, that's not too bad. Usually people pick that one up pretty well. The quotient rule kind of sucks, I'll be honest. People don't love the quotient rule. As you can see, it's quite a bit more complicated than the product rule. Most people, by the time they do 2 or 3 of the product rule problems, you'll have that formula memorized. You won't even have to worry about it. You'll just sort of know it. The quotient rule is a little bit more complicated, largely because notice there's a subtraction in here. Our formula in the product rule was a plus. So actually, if you get the two terms in a different order, it's not a big deal. You'll still end up with the same polynomial in the end. But in the quotient rule, we have a minus, meaning if you put the wrong one in front, then it'll be wrong because you'll be subtracting the wrong thing. Like 4 minus 5 is not the same thing as 5 minus 4, right? One's 1 and one's -1, and negatives make a big difference, right? If your bank, a lot of times students will say, oh, well, I was only off by a negative. But if you go to the bank and your account balance is off by a negative, is that a little mistake? No, that's like a big deal, right? So negatives are a big deal. So here you take the function that's the denominator. So they have u as the numerator, v as the denominator. So basically you're taking, say, a rational expression. You're taking the derivative of a rational expression, for example. So you take the piece that's on the bottom and multiply by the piece on the derivative of the piece on top. Subtract from that the piece on top times the derivative of the bottom, all over the denominator squared. So if you like that kind of thing, there are like little, I don't know what you call them, limericks or little like rhymes that can help people remember this formula. If you're that type of person, you can look them up and get yourself a little rhyme to help you remember this. If not, otherwise just learn the formula, right? You'll just kind of learn it when you do it a few times. So here's an example. Here's the rational expression x cubed plus 2x minus 1 over x squared minus 1. And the derivative says you take the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And you can see they just plug those in, right? They take the top function, the bottom function, and they're just plugging in the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. You get kind of a big mess, but guess what you do whenever you have polynomial terms and it's a big mess? You just simplify everything, combine like terms, go from there, and eventually you end up with this. This would be your derivative, okay? So the quotient rule generally makes things a little bit messy. They can, most people don't really enjoy doing the quotient rule. There are tricks sometimes where you can turn a quotient rule into a product rule, but they also require some steps we haven't learned yet. So we'll look at that maybe today. We probably have time to get to it today. We'll take a look. Okay, where's that next problem I wanted? So you'll practice the product rule, you'll practice the quotient rule, you'll be good. Those aren't too bad. I mean, the quotient rule is no fun, but like it's doable. Okay, let's look at the next one, which is 2.3. Higher order derivatives. So, as you may have sort of already pieced together from the fact that I told you the cutoff for the test, the last two sections you learn, if you're watching, one is called the first derivative test, the other one is called the second derivative test. So you may have already started figuring out, oh, maybe there's more than one derivative. And the answer is, we can just keep taking derivatives. Sometimes that is valuable. So if you look at the number of primes here, that's the order of that derivative. So in other words, if you have a function and you take the derivative once, that's what we call the first derivative, and that's f prime. If you take the derivative of the derivative, that's called the second derivative, or the second order derivative, and we use f prime prime. If you then take the derivative of that, then you have the third derivative. That's f prime prime prime, right? And then we can just keep taking the derivative And at that point, you don't want to be writing out 17 apostrophes, right? So at some point, we just switch to putting a little number up there to get the fourth derivative. Now, why would you do this? Why on earth would we take the derivative of a derivative? Well, this actually makes a lot of sense. So you've got, remember the derivative is giving us a rate of change, right? So let's see. Well, let's see. Why would you keep taking the derivatives? Well, think if we had, let's say you go for a drive. You get in your vehicle, you go out on the road, and you're driving. And we are able to keep track of your distance, say from Ventura, at any given time along your drive. So we end up with a function that tells us your distance from Ventura at 1 minute and 2 minutes. That's what our function is telling us. At any given time, we know how much distance you've covered. Well, what is that? What if we take the derivative of that? If we take the derivative of your position, so that's the rate of change of your position, well, that's what we call speed or velocity, right? If you think about it, that's what you're doing. When you're driving down the freeway and you look at your speedometer, what is it telling you? It's telling you the rate of change of your position. If it's saying that you're going 75 miles per hour, that's the rate at which your position is changing. You are changing your position by 75 miles in an hour, right? So if you start with a position function, the derivative is speed. You go, okay, well, that's helpful, but why would I take the derivative again? Well, if you took the derivative of the derivative, so if the first derivative, your first function is position, we said your first derivative is speed. Well, if you take the derivative again, then you're figuring out the rate of change of your speed. Well, what do we call that? What do we call that when we measure the rate of change of someone's speed? That's acceleration, right? So, and acceleration comes up when people compare cars they want to buy. Well, this car has really good acceleration. Or if you're trying to shoot a rocket into space, then you have to know the acceleration it can undergo because it has to reach escape velocity, right? So acceleration is the second derivative of the position function. So there's lots of reasons why you would want to take the second derivative. And in physics, they even go one step further. A lot of times, I mean, they go many steps further, but sometimes they even want the third derivative. In physics, this is called the jerk. It's the derivative of acceleration. So you have position, you take the derivative, you get speed. Take the derivative again, you get acceleration. And then you want to know how your acceleration is changing over time. And in physics, that's called jerk. Okay. So they're just asking you for higher order derivatives, and you're just going to basically keep taking derivatives the appropriate number of times to get the one that they want you to do. So by this point, you can take derivatives of a bunch of different types of functions and figure those out. This one seems... So you can see here you have a problem. They're going to have you interpret higher order derivatives. So just like I walked you through with position, the derivative of that is speed, the derivative of that is acceleration. There's problems in the book where you're going to have to think about, well, what does that mean in these different cases, right? Right. So that one's not too bad. That one's a little more straightforward. Just take higher order derivatives and then be able to interpret them. Okay. Then we get into stuff that starts to get a little bit more complicated. So 2.4. This is called the chain rule, and this one throws people for a loop. It's confusing to people. I remember being kind of confused by it the first time I saw it and wasn't really sure like when to use it. And that's part of the problem, is people will just forget to use the chain rule entirely. So you have to remember to use it, and then when you use it, once you get the hang of it, it's not too bad, but when you're first learning it, it takes a little bit. It takes a little bit to make sense of, and the notation definitely does not help understanding. Okay, so let's see. This says so the chain rule, if y is a differentiable function of u and u is a differentiable function of x, that is y, oops. My allergies are getting bad. My throat's all messed up. Excuse me. So if y is a differentiable function of u and u is a differentiable function of x, that is y is equal to f of u and u is equal to g of x, then y is equal to f of u equals f of g of x, and y is a function of x. So I get that was totally confusing what I just said, right? Probably the notation looks like aliens wrote it. It's all very confusing. Basically what we're talking about is composition of functions. So you did this in algebra class. When we have a function that is buried inside of another function, sometimes we will have the benefit of knowing what those buried functions are. Sometimes we will not. And that happens in the real world. Sometimes you get all the information you want and the problem's easy. Sometimes you do not get all the information you want and the problem is hard. So this is one way of writing it in one notation. dy dx is dy du. So the derivative of y with respect to u times the derivative of u with respect to x. I think the more popular version that people like is this version here, the second one, dy dx. If we have a composition of functions, we take the derivative with respect to the outer function, leaving the inner function the same, multiplying by the derivative of the inner function. So let's see what that would look like. Let's work through a couple problems. These will be easy enough. I can write them out instead of just those difference quotient problems. One are a mess to try to write out by typing. So that's why I was just showing in the book. But we'll type some out that are the chain rule. So chain rule. So let's say we've got if f of x is equal to, say, 2x squared minus 5x plus 1 raised to the 51st power. Then okay, so let's take a look at this and try to understand that this is a composition of functions. So that means one function is buried inside of the other function. So what do we have here? Inside the parentheses, we have a polynomial, 2x squared minus 5x plus 1. And then we have another function on the outside that says whatever's in the parentheses, raise it to the 51st power. Okay, so two functions. We have a composition of functions here. This is different than when we did the product rule a little while ago, where you have two different functions and you multiply them together. This is where we have two functions, but one is embedded inside of the other one. Okay, so you don't want to mix those up. Sometimes people get confused between the two. Now, theoretically, we could do this as one big polynomial. All you would have to do is take 2x squared minus 5x plus 1 and just raise it to the 51st power. Well, nobody wants to do that because, first of all, it's a really annoying calculation to do. But also, you would end up with this massive, massive polynomial, which would be really difficult to read because there would be like about 50 terms in it. No one wants to write a polynomial with 50 terms in it, right? You probably make a mistake somewhere. It's just not a good way to go. So not only does this make the problem, the chain rule will make this problem a lot easier to do, it's also going to keep it in a nice compact form, which will be much easier for us to write. Okay, so let's try to make sense of that chain rule then. What was it saying? It was saying, all right, let's go back to it and look at it. This is saying if you have something that's written as f of g of x, so g of x is embedded inside of our function f, then we first take the derivative with respect to the outer function f, leaving the inner function g the same. Then we multiply by the derivative of the inner function. This is called the chain rule. So let's do that. This says then, okay, I am going to take the derivative with respect to the outer function. Well, the outer function is that we're raising something to the 51st power. So remember, our power rule says I bring the 51 down in front and I decrease the exponent by 1. So this would become 51 times 2x squared minus 5x plus 1, because we're keeping the g of x the same. And we decrease the exponent by 1, so we raise it to the 50th power. So we're not done. We're not done with the problem. This is kind of a mistake people make, is they do this first step and then they think they're done, but they're actually forgetting the chain rule piece. So before we go ahead with the rest of it, I've brought the 51 down in front, and we decrease the exponent by 1. We use the outer function in this example is the power rule. Right? The outer function is the power rule. So we take the derivative using the power rule, leaving the inner function the same. And then we multiply by the derivative of the inner function. So now I'm going to multiply by the derivative of 2x squared minus 5x plus 1, which is 4x minus 5. So here's that chain rule piece on the end that people forget, but it makes a big difference, right? So if your function is 2x squared minus 5x plus 1 to the 51st, then your derivative is 51 2x squared minus 5x plus 1 to the 50th times 4x minus 5. See how, again, nice compact way of writing this? It's not a polynomial with 50 terms in it, right? That's not what it is. So pretty easy for us to calculate. Also, it's a nice compact way of writing the thing. Okay, so you'll have problems like that where you're composing, it's composition of functions, and you're using that chain rule to take the derivative, basically. So the chain rule, people find it annoying at first, but in the long run, it actually is kind of your friend. It makes these problems, once you understand how to use the chain rule, it actually makes them way easier to do, right? So we want to keep that in mind. Let's double check here where I wanted to go here. And then here, towards the end of the section, you start seeing the more complicated ones. This problem has a few things going on. You're going to do a product rule, but you're also going to do a chain rule inside of your product rule, right? So watch the video and just realize, oh, there's a product rule going on. There's some power chain rules going on based on the power rule. There's a few things taking place there. Let's look at this one first. So let's work through this example and try to make sense of it. For temperatures greater than 10 degrees Celsius, the average daily number of soft drinks sold, S, in hundreds, in a city depends on the temperature T, as S of T is equal to 1200 plus 23T plus 600 times T minus 10 to the 1/3. So that looks complicated, and it is. But these are the kind of things that people can figure out, right? You start to look at one variable, and it allows you to start to predict things about other variables. For instance, right, there's all sorts of things that can be predicted now, especially as we get more and more data for things, and AI is getting better at making predictions about things. Um, things kind of started changing, like with Google. Google was kind of when we first started being able to collect massive amounts of data, and Google started making predictions about where there was going to be flu outbreaks. And people thought this was kind of weird at first. How could a search engine figure out where there's going to be flu outbreaks, right? How is how is the place that I go to look up, like, where should I, where's a restaurant downtown? How is that going to tell me where there's flu outbreaks? Well, what Google figured out was if they look in cities and realize all of a sudden people Googling flu symptoms, as that goes up, about 10 to 14 days later, you're going to see a big outbreak of flu in that city. So Google would start telling cities, hey, you're about to have a flu outbreak. You better prepare for it, and get people medical, a lot of older people die from flu and stuff like that. So a lot of times we can take one variable and connect it to another variable, right? This is what people do sometimes when they're trading commodities, is they figure out, next year is going to be extra hot, and so that's going to make the price of certain things go up, and then they buy futures in those things, and then when the price goes up, they sell their futures, and they make a bunch of money, right? So we like to be able to take trends that are out there and be able to make predictions about what our company is going to do. So one pause before we jump into this. So there's a question about the chapter test. So we talked about that earlier. Where was it? It says in here, if you forget, it says here in class, we're going up to the second derivative test. So if you go to that exam 1 preparation, it says the exam will cover everything up to and including the second derivative test, which is in that chapter. So everything on Canvas before where it says second derivative test is fair game, which is right here in chapter 3, actually. So it's basically the middle of chapter 3. Okay, if you want a more detailed explanation, watch earlier in the video, right? Because I explained that a little bit. Okay, so where are we with this problem? So we've got our function that relates temperature to the number of soft drinks sold, which makes sense, right? As temperature goes up, people sell more ice cream, they sell more soft drinks, they sell all sorts of stuff. The number in hundreds of soft drink aluminum cans recycled R depends on the number of soft drinks sold, S, as R of S is equal to S to the 3/4. So we have two functions here. We have a function telling us about soft drinks being sold based on temperature, and then we also have the number of cans being recycled based on soft drinks sold. So what that means is if we could tie these two functions together, we would actually have a function where we could relate temperature to the number of cans recycled, right? Because that's sort of jumping from beginning to end of this track of temperature tells us about soft drinks. Soft drinks tells us about recycling. So then temperature should tell us about recycling, and it does, right? So give some reasonable numbers for the domain of the function of S. Okay, so what do we think about S, right? Notice this. What if I just throw this into Desmos and assume that there isn't really a domain, right? We just say, the domain could be anything. So let's look at it. That's going to be S of t, f of t equals 1200 plus 23t plus 600 t minus 10 to the 1/3. Okay, so the question they're saying is, we'll take these one at a time, right? that function takes, it's going to take a long time to come down. Let's look at the other one. Well, okay, so let's just think our way through this. The number in hundreds of soft drink aluminum cans recycled R depends on the number of soft drinks sold S. So we want to know about the function S. Well, notice that it can go negative here, and like, what would the domain be? Is it possible for the temperature to be less than 0? Yeah, the temperature could be less than 0. But here they tell us for temperatures greater than 10 degrees Celsius. So actually our function, they're telling us that the function isn't really relevant if you're not at least 10 degrees Celsius, right? You can graph the function. We can see it over here. If we graph it, it exists for t values less than 10, but they're telling us in the problem it doesn't make sense. The temperatures need to be greater than 10. Okay, so it needs to be at least 10 degrees Celsius. Well, what's the maximum? They're talking about reasonable numbers. Well, does it ever get to 1,000 degrees Celsius? Well, not like where we are, right? Maybe on the sun, but not here, like on the surface of the planet. So we might be tempted for me to just keep going out and picking higher and higher values of X, or T, I guess in this case. But really, you reach a point over here where you're like, we don't need to go past that because it's not going to be 110 degrees Celsius. Sort of humans would not exist, right? Because we're talking Celsius here, not Fahrenheit. So your goal, what they're asking you about, is how do you come up with a reasonable value for that? So people tend to, here's their answer. People tend to drink more soft drinks on hot days than on cold days. If we restrict the domain of this function so that T ranges from 20 degrees Celsius, which is 68 degrees Fahrenheit, to 40 degrees Celsius, which is 104 Fahrenheit, we should have a reasonable range of values to input the temperature. So that might be okay. Maybe. I mean, this weekend where my family lives, it's supposed to be like 108. So maybe you'd want to up that a little bit more. Notice that in the problem, they told us that it's for ranges bigger than 10 degrees Celsius. That would be a reasonable cutoff. You could make a justification for why it should be 10 degrees Celsius. But here in the problem, they're saying, well, if it's below 68, people aren't probably going to be that thirsty drinking a lot of sodas. So why don't we just start at 20 degrees Celsius? And this is one thing you want to realize about math. There's not always an exact right or wrong answer. Like, people will tell you that. Oh, well, in math, there's always a right answer or a wrong answer. Well, not really. Like, that might be true if you're just solving an equation in algebra. But when you're doing real-world problems, there's room for people to interpret problems differently. Some people may think, like me, I would say 104 is not enough, right? Because I might be going to a place this weekend where it's going to be 108, right? So maybe I think it should go higher than 40 degrees Celsius. But you want to be able to justify the decisions that you're making. We're not just randomly picking values and going, well, one number is as good as another, right? I have a justification for saying 40 degrees Celsius is not enough. I think it should go to, say, 42 degrees Celsius or 43 degrees Celsius, but I can justify that with a reason. That's important. Okay, part B. How many cans can be recycled when the temperature is 27 degrees Celsius? And I'm kind of getting crunched for time here. So the number of cans when it's 27 degrees Celsius, one way to do this would be to take 27, put it through your function S. Whatever you get out, you then put that through your function R and see what you get. And that's what they did here. 27 goes through our first function. You get out 3,364. You put that through the second function. You get 442, right? So then you get your answer. Okay, so you just kind of think about it. Here's a picture of it, kind of how it works. How does the number of cans recycled change as the temperature changes from 27 degrees to 28 degrees Celsius? So in this case, this is kind of back to our... So they're asking how does it change? So that's the derivative, right? So we're using the derivative to figure out that rate of change. And then they give you an interpretation here. This is like that marginal analysis. So they do it at 27, and they use that marginal analysis interpretation. So if the temperature in the city increases by 1 degree Celsius from 27 degrees to 28 degrees, the number of aluminum cans recycled in the city will increase by approximately 524. Okay, so you're doing that, and then what was the last part? D. Suppose we want to use Fahrenheit temperature scale instead of Celsius scale. How would you change the problem? Basically, you'd have another function in there that is your conversion formula. So you now would have, instead of a composition of 2 functions, you'd have a composition of 3 functions, and then you would work it all out that way. Okay. So as we wrap up here, let me close this thing. That's the little arrow. There we go. We'll close that down. So, so your test is going to cover everything up through the middle of Chapter 3. You've got a few things coming up. You've got your Exam 1 preparation discussion that you want to look at that includes your study guide in there. Remember, it goes a little past Chapter 3, which also, remember, means you're going to want to work ahead of where the homework is due. Your Chapter 3 homework is not due until the 7th, but most of you will have already taken your test by then. So at least 3.1 and 3.2, you want to try to do earlier in the week, right? Maybe even by Sunday. That way you have it done. If you're taking the test Monday, you've done 3.1 and 3.2 before that. If you have not made your appointment yet for the testing center, you're sort of in danger. You're gambling with your grade. I would make it immediately. And you'll find the information by going to exams, clicking that. You've got your link to the testing center, and then they've got their student request form over here, and you can contact them and get that taken care of. The school is totally closed on the 4th. It is a holiday, so you cannot do anything on campus on the 4th. We will not have class on the 4th. I'm not allowed to conduct class on the 4th. It is a class holiday. I cannot require you to come to class. So no class. So that means we'll meet this Thursday. So in 2 days we'll meet, but then after that we won't meet for a week. So you want to make sure you're moving through this material and making sense of it. So next time when we meet on Thursday, we'll talk about Chapter 2. We'll also talk some about Chapter 3 so that you can start getting that stuff taken care of. So lots of stuff going on. I know when you take a math class in the summer, it's like there's just lots going on, and it's all very fast. So pay attention to those homework due dates. Pay attention to your Canvas discussion due dates. Right, at Exam 1 prep, where you can form study groups. You can talk about how you're going to prepare, read other people's responses to see what they're going to do, see if you can pick up any ideas from there. And that's where we're going. So I know I had some people that wanted to meet me after class and ask some questions. So I will be available in Zoom to answer questions basically until no one's left asking questions. Once there's no more questions, I'll close the meeting down. So I'm going to close down the I'm going to close down the YouTube stream. If you want to come talk to me in Zoom, come do it, soon. If no one's there, then I'll close it. But if you want to come talk to me, go ahead and do that. All right, thanks everybody. I'll see you later.